Damn, I feel alive. No more stressing out, no more messing around, no more getting by.
Here we go. Charge!
In nature, pure carbon exists as two allotropes, diamond and graphite. Beautiful transparent crystals of diamond are macromolecular crystals formed by covalently bonded carbon atoms. Each sp3 hybridized carbon atom is surrounded tetrahedrally by 4 other carbon atoms. This structure repeats itself over and over to give a giant macromolecular structure. Since carbon-carbon bonds are strong, diamond is the hardest material known to man. The melting point of diamond is very high, 3,350 degrees Celsius.
The film used in cameras contains a light-sensitive substance that undergoes decomposition under the influence of light. Photographic film is a so-called negative material. As a photograph is taken, the film is momentarily exposed to the light reflected by the object being photographed. At this stage, microscopic silver particles are produced, forming a latent image. This image becomes visible when the film is developed. The film is taken out of the camera in a darkroom and immersed in a developer solution. The developing substance causes the rapid conversion of silver ions to metallic silver within the exposed grains of silver bromide, while the unexposed grains remain unchanged. A developed photosensitive material shows a variety of tones which correspond to the intensity of light to which it was exposed. The strongly exposed areas are black. Slightly exposed ones are grey, while the unexposed ones are white. That is how a black and white photographic negative is produced. The silver salt particles that were not decomposed by light or developer are removed using a fixer, a solution of sodium thiosulfate. The positive image, or print, involves repeating the whole process, using the negative obtained as a covering object, while exposing a piece of photographic paper to light.
Alrighty then.
It's new. It's now. It's Flash Cube. Flash Cube? Flash Cube. Only with the newest Kodak Instamatic cameras. 4 full-power flashes and 1 tiny cube. Flash Cube. It's this way, man. Drop in the film. Get yourself a Flash Cube. Pop it on. Take 1. Take 2. Take 3. Take 4 flash pictures without changing bulbs. In color, of course. Newest Instamatic camera outfits from less than $18. Only from Kodak.
alkanes are numbered in such a way that the sum of the numbers indicating the positions of side groups is the lowest possible. For example, carbon atoms in this hydrocarbon can be numbered from left to right or from right to left. The first way is more appropriate, since it gives the position of the methyl group as 3, which is lower than 4, using the other numbering scheme. The name of the compound is therefore 3-methylhexane. In the case of mono-substituted cycloalkanes and arenes, giving the position is not necessary, since all the carbon atoms in the ring are equivalent. However, if 2 or more groups are attached to the ring, the numbering always starts at one of them and continues around the ring to give the lowest possible numbers. Often, the ring is treated as the side substituent when naming an organic compound. The names for such groups are derived in the same way as for alkyl groups, with the exception of the benzene ring. In this case, the group is called a phenyl group. For example, the name of this hydrocarbon is 2-phenylbutane.
Consider a molecule of carbon dioxide. Both of the carbon-oxygen bonds are polar, with negative charges located on the more electronegative oxygen atoms. The dipole moments of the individual bonds can be represented as vectors pointing towards the more negative atom. To find the dipole moment of the whole molecule, we must add the individual moments as vectors. Since they are identical in magnitude but point in opposite directions, they cancel each other out. Carbon dioxide has no net dipole moment and is a non-polar molecule.
I am a duck, bent on self-preservationum. Wait! I haven't tried toadying, kowtowing, or butt-kiffing yet! I'm still begging here! Hey!
A molecule of alanine contains a carbon atom bonded to 4 different substituents: a carboxyl group, an amino group, a methyl group, and a hydrogen atom. An atom like this is referred to as an asymmetric carbon atom. The arrangement of all the groups around the asymmetric carbon atom is tetrahedral, since carbon assumes sp3 hybridization. If we reflect this molecule in a plane, we obtain a mirror image of the molecule that cannot be superimposed onto the original molecule. Molecules that show this property are referred to as chiral. 2 mirror molecules of alanine are built of identical atoms linked together in exactly the same way. They differ solely in the arrangements of atoms in space, so that they are stereoisomers. The type of stereoisomerism shown by alanine is referred to as optical isomerism, since both isomers rotate the plane of plane polarized light in opposite directions. 2 isomers of a chiral compound, differing only in the arrangement of substituents on an asymmetric carbon atom, are called enantiomers. Notice that glycine is not chiral and does not form enantiomers, since the molecule and its mirror reflection are identical.
Electronegativity is a measure of the ability of an atom within a chemical compound to attract electrons. The more electronegative element becomes negatively charged, while a positive charge forms on the less electronegative element. In the extreme case, the separation of charge leads to the formation of an ionic bond. Fluorine, with its electronegativity of 4, is the most electronegative element. The least electronegative element is cesium, which has been assigned an electronegativity value of 0.7. In graphite, carbon atoms are hybridized sp2. The atoms are linked together by covalent sigma bonds to form 2-dimensional sheets of hexagonally arranged atoms. Each carbon atom uses 3 of its 4 valence electrons for covalent bonding. The 4th electron from each atom forms part of a delocalized cloud of electrons extending above and below the plane of carbon atoms. The planes can slide over one another, so graphite is much softer than diamond. Graphite conducts electricity, since the delocalized electrons are free to move between the planes.
Nano World. What is nano? Nano is a unit for measuring the extremely small. Nano size is measured in nanometers, which is 1/billionth of a meter. How much is a billion? For example, let's look at an emperor penguin. Let's zoom in on the emperor penguin's skin. This tick is about 1/1000th of a meter. The bacterium attached to the tick is about 1/1,000,000th of a meter. And there is the bacterium's DNA. The DNA's radius is about 1/1,000,000th of a meter. That is 1 nanometer. DNA is made up of many atoms, and atoms make up all matter. This is the nano world. This nearly invisible world can be viewed with an atomic force microscope.
Let's make the almost inconceivable nano world conceivable. The naked eye can see the diameter of a human hair. That's 1/10 of a millimeter, or 100,000 nanometers. To understand the small, we're going to scale it up to skyscraper proportions. And return to our human hair and blow it up to the size of the Empire State Building. A typical human cell, say a red blood cell, would rise to the 10th floor. A bacteria cell, the 3rd floor. Working down our scale, a run-of-the-mill protein molecule would be the same height as a small dog, about 1.5 feet. And a nanometer, on our Empire State scale, it's less than 1/4 of an inch. That's about the size of 5 microscopic atoms placed end to end.
Let's talk